Inside the world's largest nuclear fusion reactor, a group of engineers is attempting to solve one of science's most challenging challenges: how to invoke the power of a star in a seemingly inconspicuous collection of industrial structures somewhere in the southeast of France. If they succeed, they will immediately address humanity's most existential issues, drastically reducing hazardous pollutants and combating rogue climate change. That is a big if, though. Hey guys, how are you doing today? Before we proceed with this video, don't forget to subscribe to our YouTube channel. Kindly click on the notification bell to get updates on our exciting content. So come along today as we embark on a high-intensity journey inside the biggest nuclear fusion reactor in the world. Last summer, a significant milestone was reached on a science project with such a broad scope that was first started in 1985. Because the so-called ITER, or International Thermonuclear Experimental Reactor, eventually started technical construction in July 2020. The most expensive and complicated engineering undertaking ever attempted by humanity is located just outside the tranquil 10th century town of Saint-Paul-de-Guérans, État. Its main component is estimated to cost $25 billion and weighs as much as 3 Eiffel skyscrapers, even though pessimistic estimates put the real number as high as $65 billion. So what is ETA in reality? The largest and most sophisticated nuclear fusion reactor the world has ever seen is being built by an international multidisciplinary team. For many years, experts have argued that if properly harnessed, nuclear fusion could offer humanity a practically limitless supply of clean, safe energy without producing belching hydrocarbon fumes or stubbornly indestructible radioactive waste produced by other less effective methods of power generation. How does nuclear fusion function then? Nuclear fission is the mechanism used in conventional nuclear power reactors. Unintended neutrons strike bigger atoms in a fission reactor, usually uranium or plutonium, causing them to split. That dramatic chain reaction we're all familiar with from catastrophe movies and terrible old-school videos of enormous bombs going off is caused by the release of energy and even more neutrons, which in turn divide even more atoms. In a conventional nuclear power plant, the heat produced by that runaway reaction causes water to boil, creating steam that powers turbines to produce electricity. Fusion, despite the unfortunate seeming similarity, fission is a completely separate process. In a fusion reactor, a bigger element, usually helium, is created by the fusing of 2 or more lighter elements, often hydrogen isotopes. Every star's core is currently undergoing this exact same chemical reaction. In addition to providing millions of times more energy than dirty, old-fashioned fossil fuels, fusion is capable of producing 4 times as much energy as fission. Why aren't all nuclear power plants fusion-based already? This is a reasonable question to pop at this stage. 3 extremely demanding requirements must be met for fusion to occur. Before fusion can even possibly occur, the temperature in the reactor core needs to be raised to approximately 150 million degrees Celsius. That process requires a lot of energy just by itself. Second, there must be enough density in the plasma in which this reaction takes place for fusion to be likely. Third, this plasma must be contained for a sufficient amount of time so that the power generator may be effectively used. To do this, ETA engineers are currently putting together a massive structure known as a tokamak. Soviet nuclear researcher Igor Golovin first suggested this device in 1957. Since you asked, Tocomac is a Russian acronym that means toroidal chamber with magnetic coils. It's essentially a huge steel donut where extremely powerful magnets work together to generate enough heat and pressure in a vacuum to transform gaseous hydrogen fuel into a plasma. The largest tokamak ever built is located at ETA. In essence, each of its 18 massive D-shaped toroidal field coil magnets weighs 310 tons, which is equivalent to the weight of a fully latent jumbo jet. That's before we consider its 6 colloidal magnets and its enormous central solenoid, which is capable of lifting an aircraft carrier in theory. All of this is possible in a tokamak chamber that is 10 times larger inside and twice as big externally than anything that has been done before. The largest helium refrigeration unit in the world is being produced concurrently in order to maintain the largest superconducting magnet system ever operating through 100,000 kilometers of niobium-10 superconducting wires. In order to put everything in view, the ITER facility will eventually house one of the universe's hottest locations, 150 million degrees Celsius, in the reactor chamber, as well as one of its coldest, minus 269 degrees Celsius, or 4 kelvins, in the coolant system. As if conjuring the power of a real star wasn't challenging enough, ETA is also a challenging international collaboration involving almost 35 nations. To be put together on site, each person assembles their own parts. This poses some challenging logistical issues, as you can anticipate. Shipping is taking place from as far away as South Korea for some of the estimated 10 million parts that will make up ETA. Some parts are 4 stories high and weigh 900 tons. A road that leads to Fossomé-Marseille, the closest Mediterranean port to ETA, has been specifically rebuilt at staggering expense. The international effort, which has input from the European Union, the United States, Russia, China, and India, among others, guarantees stakeholders precious experimental data and access to any intellectual property produced as a result of the project in exchange for their participation. The project has 5 specific goals when ETA finally completes this massive, devilishly difficult jigsaw puzzle. The first is to use a fusion reaction to generate 500 megawatts of power. A smaller tokamak known as Joint European Torus, JET, in Culham, England, set this record back in the 1990s. JET currently holds the record at just 16 megawatts. To even accomplish this, though, the JET crew needed 24 megawatts of heating power, essentially an 8 megawatt net loss. At ETA, it is intended to apply such approaches to increase the reactor's internal temperature to 150 million degrees Celsius in the hopes that its plasma will be able to sustainably burn with only 45 to 51 megawatts of input heating power. If they succeed, it will mark the first time that fusion has produced more power than was used by a healthy factor of 10. The second goal of ETA is to show that the several related technologies required to support a fusion reactor are feasible. This entails heating the complicated diagnostic systems, the massive cryogenic apparatus used to keep the magnets cool, and routinely tedious tasks like maintenance and control systems. The third goal of ETA is to achieve so-called blazing plasma, which is its ultimate goal. That is a fusion process that can last longer than is now feasible because it produces heat on its own. To demonstrate the viability of so-called tritium breeding, the fourth aim is likely the most crucial. It has long been known that a combination of deuterium and tritium is the most likely fuel for reliable fusion reactions. As luck would have it, seawater contains a huge amount of deuterium, naturally occurring. On the other hand, there is typically only 3.5 kilograms of tritium available in nature at any given time, not even close to enough to support the anticipated fusion energy growth. In order to hopefully capture and produce tritium as a byproduct of the fusion reaction itself, resourceful ETA engineers lined their reactor wall with a sophisticated breeding blanket made of lithium-based materials. The fifth and final goal of ETA is to demonstrate the safety of a fusion device, which is essential in a society where outspoken opponents of nuclear energy exist. The ETA project is finally at the construction stage and anticipates firing up its first plasma in December 2025, following many years of delays and changes in top staff. If all goes according to plan, 3 processes will combine to get the core's temperature up to the magical 150 million degrees Celsius needed for fusion to take place. These are ohmic heating, something akin to your home microwave produced by deft management of those powerful magnetic fields, neutral beam injection of high-velocity charged deuterium, and high-frequency electromagnetic waves. Additionally, while other tokamak fusion reactors have been accomplished, ETA will be the first to produce more energy than it consumed. It should be stressed that ETA will never be linked to the electrical grid. Even if the project succeeds, it's merely a lengthy, multi-decade proof of concept to determine whether it's possible. Due to this, some critics have branded the project a costly waste of money, suggesting that money would be better spent on competing initiatives like the so-called Stellarator, but that's a different tale. We salute the best minds in nuclear physics who are currently doing their hardest to conjure a star. How do you feel? Is humankind's only safe path to a sustainable future nuclear fusion? Or is the ETA team interfering with forces outside of our control? Tell us in the comments section below. If this video is insightful for you, then go on and like the video. Please kindly subscribe to our channel and click on the bell button for more of our updates.